You already know that teaching an AI to truly see, and I mean profoundly understand space and time, not just slap a label on a picture, is literally one of the most exciting frontiers in AI right now. So let's get right into it. The fundamental challenge of modern AI vision is essentially a giant balancing act. How exactly do we teach an AI to see both the forest and the trees in a highly complex, moving video? Honestly, it's relatively easy for an AI to grab the big picture, the semantic, global context of a scene. But the moment it needs to track fine-grained, dense local details, like exactly where a specific object's edges are as it moves through space, the system just kind of loses focus. Section 1, the AI Vision Challenge. Okay, before we get into version 2.1, we have to quickly touch on the bedrock here. Joint Embedding Predictive Architectures, or JEPA. Now, unlike some related works that exhaustively try to reconstruct missing parts of a video pixel by pixel, JEPA works way smarter. It learns by predicting missing parts in an abstract latent space. It's a brilliant way to get a strong global understanding of a scene's dynamics without the massive computational overhead. But, and this is a big but, previous versions like V-JEPA 2 had a known blind spot. They really struggled with dense, fine-grained local spatial structure. Let's use a quick analogy. Picture an older video-trained AI model looking at these dogs resting on a bed. It looks at the scene and nails the categorization. It knows it's looking at a room, a bed, and some dogs. Global semantics? Check. But say a robotic arm is trying to reach out and gently pet one of those dogs. The AI would struggle to pinpoint the exact, localized spatial coordinates of a specific ear or paw. It sees the forest perfectly, but the trees are just a blur. And here is the visual proof of that blurriness, along with how they fixed it. When we dive into the analysis of V-JEPA features for dense vision tasks, things get really interesting. These PCA feature maps translate the AI's internal representations into colors. Check out the middle row. That's the older V-JEPA 2. You can literally see how fragmented and noisy the features are. The AI is clearly confused about exact boundaries. But look at the bottom row for V-JEPA 2.1. Boom! Suddenly everything is sharp, spatially coherent, and super detailed. It perfectly maps the cat's face and the diver's silhouette. It's like the AI finally put on glasses. Section 2. Unlocking dense local features. So how did they pull this off? The secret sauce here is a brand new training recipe built on 3 core concepts. Step 1 is masking, intentionally hiding patches of the video so the AI has to guess what's missing. Step 2 is a new dense prediction loss. This is huge. It forces the model to learn not just from the masked areas, but from the visible context patches too. And step 3 is deep self-supervision, providing feedback throughout all the network's layers. By explicitly supervising those unmasked regions, those tiny visual details just snap right into focus. Section 3. Inside V-JEPA 2.1 architecture. Let's look under the hood at the actual architecture. You've got the flow of information through the X encoder up top and the Y encoder at the bottom. The critical innovation to notice here is the deep self-supervision, applying the loss hierarchically. It's not just waiting to check the final answer at the very end of the line. It's actually evaluating multiple intermediate encoder layers along the way. This multi-level fusion is what creates such a richly detailed representation of the world. Which brings us to the absolute game changer here, the shift in the loss function. In V-JEPA 2, predictive loss was applied only to the masked tokens. Because of that, the AI let the visible tokens become lazy global aggregators. They basically just summarize the whole scene without bothering to map the local details. V-JEPA 2.1 flips the script by applying a dense prediction loss to all tokens. By forcing the AI to spatially ground every single patch of the image, lazy global aggregation is completely prevented, and that beautiful, fine-grained structure emerges. Section 4. Scaling data and models. To scale this architecture up, the researchers brought in some heavy artillery. First, scaling image data. They pumped in a massive dataset of 142 million curated images, right alongside the video data. To handle all that, they introduced a multi-modal tokenizer, which allows a single shared encoder to natively process both images and video in a totally unified way. And maybe the best part? Through model distillation, they packed all this power into much smaller, highly efficient variants, like the 80 million parameter V-JEPA. It makes this state-of-the-art tech far more accessible to the rest of us. Section 5. AI in the physical world.
Let's talk numbers, because the jump here is honestly wild, and it proves exactly why improving dense video SSL features matters. On standard benchmarks like NYU V2 depth estimation, V-JEPA 2.1 delivered a massive 52% improvement. And for ADE 20K semantic segmentation, it nearly doubled the performance with a 96% improvement. There is no doubt about it, this new training recipe gives the AI a profound structural understanding of its environment.
But enough spreadsheets, right? Let's show, not just tell. Check out this real-world test using a Franca Panda robotic arm moving to grab a cup. By swapping to V-JEPA 2.1, the researchers instantly saw a massive 20% improvement in real robot grasping success over the older model.
As the arm opens that parallel jaw gripper, it's blind in the traditional sense. It relies entirely on the AI's internal world model. Because V-JEPA 21 has those incredibly sharp, coherent, dense features, it encodes depth information beautifully. And if you're a physical agent trying to interact with 3D objects in the real world, accurately judging depth is everything.
Notice how the arm is continuously planning its trajectory as it lowers. What's crazy is that V-JEPA 2.1 pulls off this precise maneuvering while planning its actions 10 times faster than previous navigation models. So it's not just significantly more accurate, it is blazingly fast.
And there it is, a totally successful grasp. Keep in mind, this entire sequence is happening zero-shot in a new environment. No one exhaustively pre-programmed the robot for this exact cup on this exact table. It is dynamically generalizing its understanding of the physical world on the fly.
As it lifts the cup, it's predicting the physics of the interaction entirely in that abstract latent space we talked about earlier. By doing this, it completely bypasses the computational nightmare of trying to generate perfect pixel predictions for every future frame of video.
Finally, the arm safely maneuvers the cup. This whole sequence highlights a level of precise, short-term object interaction anticipation that was practically impossible when AI had to rely on the blurry, globally aggregated features of older models. V-JEPA 2.1 literally gives the robot the spatial grounding it needs to thrive in reality.
And the crazy thing is, grasping a cup is just the beginning. This architectural philosophy unlocks state-of-the-art performance across a huge variety of downstream tasks. We're talking short-term object interaction anticipation, action anticipation, robotic arm planning, and navigation planning. It completely dominates visual analysis too, excelling in depth estimation and semantic segmentation, video object segmentation, and even video and image classification and video question answering. It's the whole shebang. Which leaves us with a truly exciting thought to chew on as we wrap up today's explainer. If applying dense predictive loss and deep self-supervision can suddenly snap the blurry world into sharp focus for AI, what comes next? What happens when these latent world models scale even further, finally allowing autonomous robots to perceive, predict, and plan flawlessly in our physical reality?